Hello and welcome to Engineers Got Blood. So what we have here is a problem relating to a magnetic circuit, or shall I say an electromagnet, composed of a magnetic core, this one, and it's being excited by a DC source, so it's a constant voltage source. And on the other side we have here a moving part, and it is assumed that this material and this material are identical, and this moving part is attached to a spring, and the spring is attached to a permanent in a permanent place. So in this problem it says the relay circuit, the whole system is the relay circuit, has the following parameters. The area of the air gap is equal to 0.001 m squared, and the number of turns n equals 500, and the L, so L here is this part, the gap length, that is equal to initial length of the gap equals 0.02 meter, and the spring constant K equals 1000 Newton per meter, and the resistance of the coil probably equals 18 ohms. Now the problem is, what is the minimum DC supply voltage for the relay will make contact when the electrical circuit is closed? So this problem requires us to solve for the magnitude of the voltage supply such that this magnetic core would be able to allow this moving part to get attracted into it totally, or this will move totally with a displacement L equals 0.02 meter. So that requires us to solve for the force of attraction required such that this moving part will move towards the magnetic electromagnet. So the required for this problem is to solve for not the force but the voltage to be used for this electromagnet. But before solving the voltage, let us determine the force of attraction required for this moving part to move, and the force is equal to 1/2 times the flux squared times the derivative of the total reluctance with respect to x. And the R total, by the way, the condition for this problem is to neglect the iron reluctance or the magnetic core reluctance, and so only the gap produces reluctance. So the total reluctance as a function of x is equal to 2x over 4 pi, that's the mu o, times 10 to negative 7 times the area of the gap, that is 0.001, and this results to, we have 2 over 4 pi times 1 minus 7 times 0.001, so we have 1.59155 times 10 to the 9th times x, ampere turns per Weber. And let's now solve for the flux as a function of x, since as this moving part moves, the flux magnitude also change. So the flux is equal to the MMF equals 500, so the number of turns is equal to 500 times I, we don't know the excitation current. We haven't solved for the excitation current yet, so that is still unknown. All over 1.591549431 times 10 to the 9th x, and our flux now as a function of x would equal to, we have 500 all over 1.591549431 E9. So this is 3.141592653 times 10 to the negative 7 all over x. And so, okay, let's use this equation again. We have force. So the force would equal to the force exerted on the spring. That is equal to kx. So we have 1000 times the displacement x, or shall I say L. L is equal to 0.02 meters. So that's the displacement, equal to this one, this expression. We have 1/2 times flux, 3.141592653 times 10 to the negative 7 all over x squared times the derivative of this expression. That is simply 1.59155 times 10 to the 9th. Oh, I forgot the I. Anyway, so using your calculator, your advanced calculator, we may extract the value of I in this expression, this whole equation. 1000 times 0.02 equals 0.5 times, we have 3.141592653 times 10 to the negative 7. Okay, by the way, another condition. So at x is equal to 0.02 meters, so this x now would be substituted to 0.2 meters. So we can now solve for I. So x is equal to 0.02 squared. Oh, I forgot the x. Forgot to put a variable. So this is times x times 1.59155 E9. Okay, shift solve. So our calculator gives us this result. We have I, or x, equals to 10.0925 amperes. And so since we have determined or computed for the excitation current, we can now solve for the voltage, excitation voltage. So we have V equals, just simply the ohms now. We have R times I. So R is 18 ohms, the coil resistance, times the excitation current, 10.0925, and this results to times 18. So the excitation voltage is equal to 181.67 volts, and that's the answer. Thanks for watching.